According to my watch, we are right on time to start. I may be 1 minute early or something. Okay. Do you have questions out of the material we covered last time? What I'm planning on doing, let me tell you what I'm planning to do. I will cover triple integrals today, and this way you would have accumulated enough to deal with most of the problems in homework 4. You have mastered double integration by now in all sorts of coordinates, which is a good thing. Triple integrals are your friend. If you have understood the double integration, you will have no problem understanding the triple integrals. The idea is the same. You look at different domains and then you realize that there are Fubini-Tonelli type of results. I'm going to present one right now. And there are also regions of a certain type that can be treated differentially. And then you have cases in which reversing the order of integration for those triple integrals is going to help you a lot. Okay, 12.5 is the name of the section, triple integrals. So what should you imagine? You should imagine that somebody gives you a function of 3 variables. Let's call that, doesn't have to have a name as a letter, but let's call it W, being a function of 3 coordinates x, y, z, where x, y, z is in R3. Okay. And we have some assumptions about a domain D that you are working over. You have D is a closed boundary domain. Now, 3 examples that you're going to use frequently used. A sphere, a ball, actually a ball, because the interior of a sphere is, together with the shell, is the ball. Then you have some types of polyhedra in R3 of all types. And by that I mean the classical polyhedra whose sides are just polygons. But you will also have some curvilinear polyhedra as well. What do I mean? I mean, we've seen that already. For example, somebody gives you a graph of a function, g of x and y, a continuous function, and says, okay, can you estimate the volume under the graph? Right? And until now, we treated this volume under the graph as double integral of g of x, y, continuous function over dA, where dA was dx dy. And we said double integral over the domain in, projected domain in the plane. That's what I have. But can I treat it, this volume, can I treat it as a triple integral? This is the question, and the answer is, so can I make 3 snakes? And the answer is yes. And the way I'm going to define that will be a triple snake or triple integral over a 3D domain. Let's call it curvilinear D in R3, which is the volume, which is the body under the graph of this positive function and above the projected area in plane. So it's going to be a cylinder in this case. And I'll put here 1 dV. And dV is a mysterious element, that's the volume element. And I will talk a little bit about it right now. So what can you imagine? They give you a way to look at it in the book. I mean, we give you a way to look at it in the book. It's not very thorough in explanations, but it sort of gives you the general idea of what you want, what you need to do. So somebody gives you a potato. It doesn't have to be this cylinder. It's something beautiful, a body inside a compact surface. Let's say with no self-intersections, you have some compact surface like a sphere or a polyhedron. Assume it simply connected and it doesn't have any self-intersection. Some beautiful potato that's smooth. If you imagine a potato that has singularities, like most potatoes have singularities, boo-boos and cusps, and also that's bad. So think about some regular surface that's closed, no self-intersections, and that is a potato. Does it look like a potato? Oh, let's call it P from potato. No, because I'm going to use P for the partition. So let me call it D from 3D domain. This is a three-dimensional domain enclosed by a curve, enclosed by a compact surface. So think potato. What do we do in terms of partitions? Those pixels were pixels for the 2D world in flatline, but now we don't have pixels anymore. Yes, we do. I was watching lots of sci-fi and the holograms have the three-dimensional pixels. I'm going to try and make a partition. It's going to be a hard way to partition this potato, but you have to imagine you have a rectangular partition. So every little pixel will be a, if not a cube, it has to be a little tiny parallelepiped. So a 3D pixel, let me put pixel in quotes because this is kind of the idea, will have what kind of dimensions? Will have 3 dimensions, right? 3 dimensions, a delta xk, a delta yk, and a delta zk for the pixel number k. This is pixel number k. We have to number them, see how many they are. Where k is from 1 to n, n is the total number of 3D pixels that I'm covering the whole thing. So don't think graphing paper anymore because that's outdated. Don't even think of 2D image. Think of some hologram where you cover everything with tiny 3D pixels so that in the limit, when you pass to the limit with respect to n and go into infinity, the discrete image, you're going to have something like a diamond-shaped thingy, will converge to the smooth potato. So as n goes to infinity, that surface made of tiny squares will converge to the potato. So how do you actually define a triple snake integral f of x, y, z over the domain D, dx, dy, dv, dx, dy, dz? Okay, this theoretically should be what? Think pixels. Limit as n goes to infinity of the sum of the, what do I need to do? Think the whole partition into pixels how many pixels? N pixels total is called a P, script P, and the norm of P will be the highest diameter among all pixels. And you're going to say, oh, okay, what the heck, I don't understand it. I have these three-dimensional cubes or three-dimensional parallelepiped that get tinier and tinier and tinier. What in the world is going to be a diameter of such a pixel? Well, you have to take this pixel and magnify it so we can look at it a little bit better. What do we mean by diameter of this pixel? Let's call this pixel pk. The maximum of all the distances you can compute between two arbitrary points inside. Between two arbitrary points inside, we have many distances. So the maximum of the distance between points, let's call them R and Q inside the pixel. So if it were for me to ask you to find that diameter in this case, what would that be?
It's the diagonal.
It's the diagonal between this corner and the antipode, the opposite corner. So this would be the highest distance inside this pixel. If it's a cube, you see that I wanted a cube. If it's a parallelepiped, it's the same idea. So I have that opposite corner distance kind of thing. Okay, so I know what I want. I want n go to infinity. That means I'm going to have the p going to 0. The length of the diameter, the highest diameter, will go shrinking to 0. And then I'm going to say here, what do I have inside? F of some intermediate point. In every pixel, I take a point. Another pixel, another point, and so on. So how many such points do I have? N, because it's the number of pixels. So inside, let's call this as a pixel pk. What is the little point that I took arbitrarily inside the cube or inside the pixel? Let's call that Mr. xk star, yk star, zk star. Why do we put a star? Because he is a star. He wants to be number one in his little domain. He says, I'm a star. So we take that intermediate point, xk star, yk star, zk star. Then we have this function multiplied by the delta vk. Somebody tell me what this delta vk will mean, because it really looks weird. And k will be from 1 to n. So what do? You sum up all these weighted volumes. This is a weight. So this is a volume. All these weighted volumes, we sum them up from k, for all the pixels k from 1 to n. We are going to get something like this, covered with tiny parallelepipeds in the limit as the partition's norm goes to 0 or the number of pixels goes to infinity. This discrete surface will converge to the beautiful smooth potato and give you a curvilinear image. Actually, if we saw a hologram, this is what it is. Our eyes actually see a bunch of tiny, many millions of pixels that are cubes in 3D. But it's an optical illusion. We see, okay, it's a curvilinear, it's a smooth body of a person. It's not smooth at all. If you get closer and closer to that diagram, put your eyeglasses on, you're going to see, oh, this is not a real person. It's made of pixels that are all cubes. Just the same, you see your digital image of your picture on Facebook, whatever it is. If you would be able to enlarge it, you would see the pixels being little tiny squares there. The graphical imaging has improved. The quality of our digital imaging has improved a lot. But of course, 20 years ago when we weren't even born, we could still see the pixels in the photographic images in a digital camera. Those tiny first cameras, what was that, 98?
Kodak.
Like AOL cameras that were so cheap. The cheaper the camera, the worse the resolution. I remember some resolutions like 400 by 600, not black and white. Black and white would have been neat, but really nasty in the sense that you have the feeling that the colors were not even, they were blending into each other because your resolution was so small. So it was not at all pleasing to the eye. What was good is that any kind of defects you would have, something like a pimple or could not be seen in that because the resolution was so slow that you couldn't see the boo-boos, the pimples, the defects of the face or something. Now you can see with the digital cameras we have. Now we can do, of course, Adobe Photoshop, and all of us will look great if we Photoshop our pictures. Okay, so this is what it is in the limit, but in reality, in the everyday reality, you cannot take Riemann sums like that. This is a Riemann approximating sum, and then pass to the limit and get ideal curvilinear domains. No, you don't do that. You have to deal with the equivalent of the fundamental theorem of calculus from Calc 1, which is called the Fubini-Tonelli type of theorem in Calc 3. So say it again. So the Fubini-Tonelli theorem that you learned in for double integrals over a rectangle can be generalized to the Fubini-Tonelli theorem over a parallel pi p, and it's the same thing practically as applying the fundamental theorem of calculus in Calc 1. So somebody says, well, let me start with a simple example. I give you you say, Magdalenitis, you are offending us, this is way too easy. What do you think that we cannot understand the concept? I just try to start with the simplest possible example that I can think of. So x is between a and b, given, in my case, they will be positive numbers because I want everything to be in the first octant. First octant means x positive, y positive, and z positive all together. To make my life easier, I pick that example, and I say, I know the numbers for x, y, z. I would like you to compute two integrals. One would be the volume of this object. Let's call it body. It's not a dead body, just body in 3D. The volume of the body, we say it like a mathematician, V of B. What is that by definition? Who's going to tell me? Triple snake. Don't say triple snake to other people, because other professors are more orthodox than me. They will not. They will laugh, but they will not joke about it. So triple integral over the body of, to get the volume, the weight must be 1. F integrant must be 1, and then you have exactly dV. How can I convince you what we have here in terms of Fubini-Tonelli? It's really beautiful. B is going to be AB segment cross product, CD segment cross product. What is the altitude? EF, E to F. Interval E to F means the height, so length, width, height. This is the box, carry on or USPS parcel or whatever box you want to measure. Okay, so how am I going to set up the Fubini-Tonelli integral? A to B, C to D, E to F1. And now, who comes first? The Z, Y, X. So it is like the equivalent of the vertical strip thingy in double double corners, double integrals. Yes, sir.
Professor, why did you use 1 dv y1?
Okay, you will see in a second. This is the same thing we do for areas. So when you compute an area, very good question. If you use 1 here and you put delta AK, that is the graphing paper area. It's gonna be all the tiny areas. This is what summed up. Sum of all the delta AK, which means this little pixel plus this little pixel plus this little pixel plus this little pixel plus 1,000 pixels all together will cover up the area. If you have the volume of a potato, a body, dead or alive, but it shouldn't move, okay? It should stay in one place. Then, to compute the volume of the potato, you have to say the potato, the smooth potato, is the limit of the sum of all the tiny cubes of potato. If you cut the potato in many cubes, like you cut cheese, they cut a bunch of cheddar cheese into small cubes and they feed us with crackers and wine. Okay, no comments? So you have delta VK, you have 1,000 little cubes, tiny, 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 like the Lego. Okay, forget about the cheese. The cheese cubes are way too big. So imagine Legos that are really performing with millions of little pieces. Have you seen the exhibit of Lego exhibit with almost invisible Legos at the Civic Center? They have that art festival. How many of you go to the art festival? Is it every April? Something like that. So imagine those little tiny Legos but being cubes and put together. This is what it is. So F should be 1. Now, can we verify the volume of a box here? It's very easy. What do? Well, first of all, I would do it in a slow way, and you are going to shout at me, I know, but I'll tell you why you need to bear with me. So integral of 1 dz goes first, that's z between f and e. So it's f minus e, am I right? You say, duh, that's too easy for you. I know it's too easy for me, but I'm going somewhere with it. dy dx. The one inside, f minus e, is a constant, pulls out, completely out of the product, and then I have integral from a to b of, what is that left? 1 dy, y between d and c. So d minus c, right? d minus c dx. And so on and so forth, until I get f minus e times d minus c times b minus a, and goodbye, because this is the volume of the box. It's the height, this is the height, this is, no, the height is, excuse me guys, the height is, this one is the height. This is the width, and this is the length, whatever you want, okay? All right, how could I have done it if I were a little bit smarter? Right, I have a theorem, just like before, which says 3 integrals in a product. This is what Matt immediately remembered. We had 2 integrals in a product last time. So what have we proved in double integrals remains valid in triple integrals if we have something like that. So I'm going to say theorem, it's in the book, you have a proof. So you have integral from a to b, c to d, e to f. And then some guys that you like, f of x times y, g of y times h of z. Functions of x, y, z separated variables. So f a function of x only, g a function of y only, h a function of z only. This is the complicated case. And then I have, well, dz dy dx. Excellent. Thanks for whispering, because I was a little bit confused for a second. So just as Matt said, go ahead and observe that you can treat them one at a time like you did here, and integrate one at a time and pull out a constant and integrate again, or pull out a constant and integrate again, pull out a constant. But practically this is exactly the same as integral from a to b of f of x alone, dx, times integral from c to d g of y alone, dy, and times integral from e to f of h of z dz, and close. So you've seen the version of the double integral, and this is the same result for triple integrals, and it's practically what is the proof? You just pull out one at a time. So the proof is that you start working and say, Mr. Z counts here, and he's the only one that counts. These guys get out for a walk one at a time outside of the first integral inside. And then integral of h of z dz over the corresponding domain will be just a constant C1 that pulls out. And that is that C1 that pulls out. And since you pull them out in this product one at a time, that's what you get. I'm not going to give you this as a exercise in the midterm with a proof, but this is one of the first exercises I had as a freshman in my I took it as a freshman, as multivariable calculus. And it was a pop quiz. My professor just came one day and said, guys, you have to try to do this proof all by yourselves. And some of us did, some of us didn't. To me, it really looked very easy. I was very happy to prove it in an elementary way. It was nice. Okay, so how hard is it to generalize, to go to non-rectangular domains? Of course, it's a pain. It's really a pain, like it was before, but you will be able to figure out what's going on. In most cases, you're going to have a domain that's really not bad, a domain that has x between fixed values, for example, y between your favorite guys, something like f of x and g of x, top and bottom, between top and bottom. That's what you had for double integral. Well, in addition, in this case, you'll have z between, let's make this guy big F and big G, other functions. This is going to be a function of xy, and this is going to be a function of xy, and that's the upper and the lower. And find the triple integral of, let's say, 1 over d dv will be a volume of the potato. Now, I'm sick of potatoes because they're not my favorite food. Let me imagine I'm making a tetrahedron, a lot of cheese. I'm going to draw the same tetrahedron from last time. So what did we do last time? We took a plane that was beautiful, and we said, let's cut with that plane. This is the plane we are cutting the cheese with. It's a knife. X plus y plus z equals 1. Imagine it as an infinite knife that comes into the frame. Everything is cheese. The space, the universe is covered in solid cheese. So the whole thing is the Euclidean space is covered in cheddar cheese. That's all uniform everywhere. You come with this knife and you cut along this plane, pi, let's call this pi plane, and then you cut the x plane along the xy plane, yz plane, and xz plane. What are these called? Planes of coordinates. And what do you obtain? And you throw everything away. You maintain only the tetrahedron made of cheese. Now, you remember what the corners were. This is 0, 0, 0, it's a piece of cake, but I want to know the vertices. And you know them, and I don't want to spend time discussing why you know them. So, 1, 0, 0, thank you. Huh?
0, 1, 1, 0.
Yes, and 0, 0, 1. All right, great. The only thing is, if we see the cheese being a solid, we don't see this part, the 3 axes of coordinates behind. So I'm going to make them dotted, and you see the slice here it has to be really planar. And you ask yourself, how do you set up the triple integral that represents the volume of this object? Is it hard or easy? It shouldn't be hard. You just have to think what the domain will be like. And you say the domain is inside the tetrahedron. Do you want D or T? T from tetrahedron. It doesn't matter. We have a new name. We get bored of all sorts of names and notations. We change them. Mathematicians have imagination. So we change our notations, like we cannot change our identities and we suffer because of that. So you can be a nerd mathematician imagining you're Spider-Man, and you can give your name any name you want. You can adopt a new name, and this is our behind our motivation why we like to change names and change notations a lot. Right? So we have triple integral of this t. All right, of what? 1 dv. Good. Now we understand what we need to do. Just like Nitish asked me why. Okay, now we know this is going to be a limit of little cubes. If we were to cover this piece of cheese in tiny, 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 infinitesimally small cubes. But now we know a method to do it. So according to the Fubini-Tonelli type of result, we would have A between, no, X. Who is first? This Z. Z is first, Y is moving next, X is moving last. X is constrained to move between A and B, but in this case A and B should be prescribed by you guys because you should think where everybody lives. Not you, I mean the coordinates. In their imaginary world, the coordinates represent somebody's. X, 0 to 1. How shall I give you a feeling for that? Just draw this line, this red segment between 0 to 1. And that expresses everything instead of words into pictures, because every picture is worth 1,000 words. Y is married to X, unfortunately. Y cannot say, oh, I am Y, I'm going wherever I want. He hits his head against this purple line. He cannot go beyond that purple line. He's constrained, or Y. So he says, I'm moving, I'm Mr. Y, I'm moving in this direction, but I cannot go past the purple line in plane here. I need you, because if you don't, I'm lost. Y is between 0 and 1 minus X. Excellent, Roberto. How did we think about this? The purple line has equation. How do you get to the equation of the purple line, first of all? In your imagination, you plug in Z equals 0. So the purple line will be X plus Y equals 1. And so Mr. Y will be 1 minus X here. That's how you got it. And finally, Z is that Mr. Z goes from the floor all the way. Imagine somebody who is Z is a helium balloon. And he is left, you let him go from the floor and he goes all the way to the ceiling. And the ceiling is not flat like our ceiling. The ceiling is this oblique plane. So Z is going to hit his head against the roof at some point. And he doesn't know where he's going to hit his head unless you tell him where that happens. So he knows he lives at 0, and he's going to end up where?
1 minus Y minus X.
Excellent. 1 minus X minus Y. How do we do that? We pull Z out of that and say 1 minus X minus Y. So that is the equation of the shaded purple plane, and this is as far as you can go. You cannot go past the roof of your house, which is the purple plane, the purple shaded plane. So here you are. Is this hard? No. In many problems on the final and on the midterm, we tell you, don't even think about solving that because we believe you. Just set up the integral. I might give you something like that again. Just set up the integral, and you have to do that. But now I would like to actually work it out. See how hard it is. So let's see. Is this hard to work this out? I have to do it one at a time because you see, I don't have fixed endpoints. I cannot say I'm applying the problem with the integral of f times integral of g times integral. So I have to integrate one at a time because I don't have fixed endpoints. An integral of 1dz is z between that and that. So z, 1 minus x minus y will be what's left over. And then I have dy, and then I have dx. And at this point, it looks horrible enough, but we have to pray that in the end it's not going to be so hard. And I'm going to keep going. So we have integral from 0 to 1. Have integral from 0 to 1 minus x. I'll just copy and paste it, which is integral from 0 to 1. Now I have to think. Oh, that's dangerous. I have 1 minus x with respect to y. This is going to be ugly. That's a constant with respect to y. And times y. Minus integrate with respect to y. Y is y. Y squared over 2. Between y equals 0 down. That's going to save my life because for y equals 0 is 0. It's going to be a great simplification. And for y equals 1 minus x on top, hopefully it's not going to be the end of the world. That it looks ugly now, but I'm an optimistic person, so I hope that this is going to get better. I can see it's going to get better. So I have integral from 0 to 1, and now I say, okay, let me think. Life is not so bad. Why? 1 minus x is 1 minus x squared. I could think faster. You could think faster than me, but I don't want to rush. 1 minus x squared over 2. So it's not bad at all. Look, I'm getting this guy who is beautiful in the end when I'm going to integrate. And you have to keep your fingers crossed for me because I don't know what I'm going to get. So I get integral from 0 to 1, 1/2 out, 1 minus x squared dx. Is this bad? Can you do this by yourselves without my help? What you gonna do? X squared minus 2x plus 1. That's the square.
Just change it.
Huh?
Just change it.
You can do it in many ways. You can do it whatever you want. I don't care. I want you to get the right answer one way or another. So I'm going to clean a little bit around here. It's dirty. You do it. You have 1 minute and I have to finish. And tell me what you get.
Negative.
No. As in the end is the number. What number? But you have to go slow. I need 3 people to give me the same answer because it's, it's like in that proverb. If 2 people tell you you're drunk, you go to bed. I need 3 people to tell me what the answer is in order to believe them. 3 witnesses.
1/6.
Who got 1/6? Raise hand. Wow, guys, you're fast. Can you raise hands again? Okay, being fast doesn't mean you're the best, but I agree you do a very good job, all of you in general. So, I believe it or word, 8 people, 9 people, 1/6. Now, how could I have cheated on this problem on the final?
It's a geometry formula still.
Right. In this case, being a volume, I would have been lucky enough. I'd say it's the volume of a tetrahedron. The tetrahedron has area of the base 1/2 the height is 1, 1/2 times 1 divided by 3 is 1/6, and just pretend on the final that I actually computed everything. I could have done that. From here, jump to here, or something. From here, jump straight to here, and ask you, how did you get from here to here? And you say, I'm a genius. Could I not believe you? I have to give you full credit. However, what would you have done if I said, compute, I don't know, something worse, something like triple integral of x, y, z over the tetrahedron T. In that case, you cannot cheat. You're not lucky enough to cheat. You're lucky enough to cheat when you have a volume of a prism, you have a volume of, and volume means this should be the number 1 here, number 1. So if you have number 1 here, you can, or I ask you for the volume and it's a prism or tetrahedron or sphere or something, you can go ahead and cheat, but and pretend that you actually solve the integral. Yes, sir.
What would that represent geometrically, the triple integral of x, y, z?
It's a weighted triple integral. I'm going to give you examples later. When you have mass and momentum, when you compute the center mass or you compute the mass, somebody gives you densities, then if you have a triple integral over rho at x, y, z, this could be f, but I recall it rho for a reason, not just for fun. And here dx, dy, dz. Very good question, and it's very insightful. For a physicist or engineer, the guy needs to know why we take these weighted integrals. If rho is the density of an object, if it's everywhere the same, if rho is a homogeneous density, for that piece of cheddar cheese, oh my God, I'm so hungry, rho would be constant. If it's a quality cheddar made in Vermont, in the best factory, whatever, rho would be considered to be a constant, right? And in that case, what happens? If it's a constant, it gets out, and then you have rho times triple integral 1 dv, which is what? The volume. And then the volume times the density of the piece of cheese will be the mass of the piece of cheese. In kilograms, because I think in kilograms because I can eat more. Okay? Actually not, no, I'm just kidding. You guys have really funny, like 2 pounds and 1 kilogram is not the same thing. Can somebody tell me why? You know it's not the same thing because the approximation. But I'm claiming you cannot compare pounds with kilograms at all.
Pounds is a measure of weight, whereas
Excellent.
kilograms is a measure of mass.
Kilogram is a measure of mass. Pound is a measure of the gravitational force. It's a force measure. So it's tricky, okay? And okay. Which reminds me, I don't know if you saw this short movie for 15 minutes that got an award at the previous Oscar last year, and there was one old lady telling another old lady in Great Britain, get 2 pounds of sausage. And the other one says, I thought we got metric because we are in the European Union. And she said, then get me just 1 meter of sausage or so. So it was funny. So it can be mass, but what if this density is not the same? This is exactly why we need to do the integral. Imagine that the density is, we have a piece of cake with layers. And then again, I see how hungry I am. So you have a layer with, and then cream, or whipped cream, or mousse, and another layer, and another mousse. The density will vary. But then there are bodies in physics where the density is even a smooth function. It doesn't matter that you have such a discontinuous function. What would you do? You just split. You have triple rho 1 for the first layer, then triple rho 2 for the second layer, the layer of mousse. And then, let's say it's tiramisu, you have another layer, rho 3, give me 3 for the top of layer of the tiramisu,
It
whatever.
will become constant.
So these are discontinuous. They are all constant though. That would be the great advantage because presumably mousse will have this the constant density, the dough has a constant, the homogeneous density and so on. But what if the density varies in that body from point to point? Then nobody can do it by approximation. Say volume mass 1 plus mass 2 plus mass 3 plus mass 4. You have to have a triple integral where this rho varies, constantly varies. And for an engineer, that will be a puzzle. Poor engineer says, oh my God, the density is different from a point to another. I have to find an approximating function for that density moving from one point to another of the body. Okay, and then the only way to do it would be to solve an intricate integral. Imagine that somebody, now it just occurred, I never thought about it, we would be measured in terms of this type of integral. Of course, people would be able to measure our mass right away. But then if you were to know the density, you cannot even know the density at every point of the body. It varies a lot. So every point of our bodies has a different material and with a different density. Okay. Huh?
So you said tiramisu, you made me know.
Yeah, because now, okay, take your mind off the tiramisu. Think about an exam, then you know.
Now
Okay.
it's sick.
Exactly. Now you need something against nausea. Let's see what else is interesting to do. I'll give you 10 minutes. How much did I steal from you? I stole constantly about 5 minutes of your breaks for the last few Tuesdays.
So the integral of
The integral of that. I think I would be fair to give you 10 minutes as a gift today to compensate. Okay, so remind me to let you go 10 minutes early today. Okay, especially since spring break is coming. We have a pretty application. We have several pretty applications. Let me see which one I want to mimic first. Yeah, I'm going to pick my favorite because I just want to. So imagine you have a disk that is x squared plus y squared equals 1 would be the circle. That's the unit disk on the floor. Okay. And then I have the plane x plus y plus z equals 8. And I'm going to draw that plane. I'll try my best. Do my best. It's similar to two examples from the book, but I didn't want to repeat the ones in the book because I want you to actually read them. That's kind of the idea. So you have this picture, and you realize that we had that in the first octave before. So I say I don't want the volume of the body over the whole disk, only over the part of the disk which is in the first octave. So I say I want this domain D, which is going to be what? X squared plus y squared less than or equal to 1 in plane with x positive, y positive. Do you know what we call that in trigonometry? Does anybody know what we call this in trigonometry? Let me put the points while you think. Hopefully you think. You're thinking about this. This is 1 in x-axis. 1, 0, 0, and this is 0, 1, 0, and this is y. If I were to go up until I meet the plane, what point would this be? Oh my God, it's horrible. What point would this be? On the, think about it.
107 and 017.
107, 1. This would be, you said 017, and this would be 107. How did you think about this? How do you know? Because it's on the y-axis, and since you are on the x-axis here, y have to be 0. So you're right. Very good. Excellent. Now, I'm gonna say I'd like to know if compute the volume of the body that is bounded above from above by x plus y plus z equals 8, whose projection on the floor is the domain. I know the volume of the cylindrical body. Cylindrical body. So how could you obtain such a, again, no, this is Murphy's law. Okay, how could you obtain such an object, such a cylinder?
Take a pencil and cut it into fourths.
Huh?
Take like a cylindrical pencil and cut it
Take
into
a
fourths.
salami, a piece of salami, cut that piece of salami into 4. Into 4 quarters. So this long, right? Long one. And then we take, we slice and we slice like that. So we have something like a quarter. How can I draw this? Okay, this is what it is. You don't see this one. You don't see this part. You don't see this part. This is curved. And here, instead of cutting with another perpendicular plane along the salami, so this is the axis of the salami. It's a salami. Instead of taking the knife and cutting like that, I'm cutting oblique, an oblique plane. And this is what this oblique plane will do. Okay?
Cut that way, then you have only squares.
So I'm going to have some oblique. I cannot draw better. I don't know how to draw better, okay? So it's going to be an oblique cut in the salami. Let's think how we do this problem. Elementarily, it will be a piece of cake. It would be a piece of cake. No, it wouldn't be a piece of salami.
It could be done.
How could we do that quickly with the calculus 3 we know?
That's the triple interval. Oh, you want to say with the double interval?
Double, triple, I don't know what to do. What do you think is best? Let's do the triple integral first, and you'll see it's the same thing as double integral. Triple integral over the S from, no, B, body of the salami, B. 1 dV. How can we set it up? Well, this is a little bit tricky. It's gonna be like that. We can say I have a double integral over my domain D. When it comes to the Z, Mr. Z has to be first. So Mr. Z says, I'm first. I know where I'm going. you guys are, x and y are bound together, married in the elemental area of the surface, of the, this is like dx, dy thing. But I am independent from you, I'm z. So I'm going all the way from the floor to what? You taught me that. 8 minus x minus y, and 1. This is the way to do it as a triple integral. But then Alex will say, I could have done this as a double integral. Let me show you how. I could have done it over the domain D in plane. Put the function 8 minus x minus y as being z from the very beginning, because that's my altitude function, f of x and y. So then I say dx, dy, dx, dy doesn't matter. That's the area element. Fine. It's the same thing. This is what I wanted you to observe. Whether you view it like the triple integral like that, or you view it as a double integral like that, it's the same thing. This is not a headache. The headache is coming next. Okay? This is not a headache. So you can do it in two ways. And I'd like to look at check the two methods of doing this. And set up the integrals without solving them. Can you read my mind? Do you realize what I'm asking? Imagine that would be on the meter. What do you think I'm asking the two methods? This can be interpreted in many ways. There are two methods. I mean, one method by doing it with Cartesian coordinates x and y. The other method is switching to polar coordinates and set up the integral without solving it. And you say, why not solve it? Because I'm going to cheat. I'm going to use a TI-92 to solve it. Or I'm going to use a MATLAB or Maple. If it looks a little bit complicated, then I don't want to spend my time. Actually, engineers, after taking Calc 3, they know a lot. They understand a lot about volumes, areas. But do you think if you work on a real-life problem like that your boss will let you waste your time do the integral by hand? Most integrals are really complicated in everyday life. So what you're going to do is going to be a scientific software like MATLAB, which is primarily for engineers, Mathematica, which is the similar MATLAB, but it's mainly for mathematicians. It was invented at University of Illinois Urbana-Champaign. They're still very proud of it. I prefer MATLAB because I feel MATLAB is stronger, has higher capabilities than Mathematica. You can use Maple. Maple lets you set up the endpoints even as functions, and then it's user-friendly. You type in this, you type in the endpoints. It has little windows here. You guys don't need to know any programming. It's made for people who have no programming skills. So it's going to show a little window on top, here, 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 here. You type those and you press enter, and it's going to spit the answer back at you. So this is how engineers actually solve the everyday integrals, not by hand. I want to be able to set it up in both ways before I go home or eat something, right? So we don't have to spend a lot of time on it, but if you want to tell me how I'm going to set it up, I would be very grateful. So this is Cartesian, and this is polar. All right, who tells me in Cartesian, which one do you prefer? I mean, it doesn't matter. You guys are good and smart, and you'll figure out what I need to do. If I want to do it in terms of vertical strip, so-called vertical strip method, first I integrate with respect to y and then with respect to x. And maybe to test your understanding, let me change the order of integrals and see how much you understood from that last time. So x is between what and what? Look at this picture. I have to reproduce this picture like that. 0 to 1, says Alex, and he's right. And y will hit his head against
1 minus x.
Square root 1 minus x squared. So we know very well what we are going to do, what Maple's going to do for us. 1 square root 1 minus x squared. And then what do I put here? 8 minus x minus 1. Can I do it by hand? Yes, I guarantee to you I can do it by hand. Let me tell you why. Because when we integrate with respect to y, I get xy. So I get xy and y will be plugged in 1 minus x squared. How am I going to solve an integral like this? I can, the first one with the table, the second one with the u substitution. And the last one is a little bit painful. I'm going to have y squared over 2, but when I square, according to Alex, yes, you're right. Maybe that is the
That's the only part you can integrate without.
and I can integrate one at a time, and I'm going to waste all my time. So if I want to be an efficient engineer and my boss is waiting for the end of the product, at the end of the day project, of course I'm not going to do this by hand. How about the other integral? Same integrand, same idea, y between 0 and 1, and x between 0 and
Square root 1 minus y squared.
square root of 1 minus y squared, because I'll do this guy with horizontal strips and forget about the vertical strips. And so Mr. Y, I will take my head and it cracks. So it means that I need some yoga. Y is between 0 and 1 or gymnastics. So x is between 0 and square root 1 minus y squared. And I'll put it here. And I'll leave it here on the meter. And I'm going to make a sample like I promised. Okay, good. How would you do this to set up the polar coordinate integral? And that is why Alex said maybe that's a pain because of a reason. And he's right, it's a little bit painful to solve by hand. But again, once you switch to polar, you can solve it with a calculator or a computer software, scientific software in no time. In Maple, you just have to plug in the numbers. You cannot plug in theta, I think, as a symbol. I'm not sure, but you can put theta as T and R will be R, or you can use whatever letters you want, the Roman letters. So you have to integrate smartly here, switching to R and theta, and think about the meaning of that. So first of all, if I put the R d theta, I'm not worried that you won't be able to get me R and theta, because I know you can do it. You can prove it to me right now. R between 0 and, excellent, and theta, pay attention, between 0 and, excellent, I'm proud. Yes, sir.
Is it supposed to be r dr d theta, or are you going to add that later?
I will add it here. So the integrand will contain the R. Now, what do I put in terms of this? I left enough room.
So is it pi over 2 or is it like negative pi over 2? Or like
And it doesn't matter because I'll take that. We assume always theta to go counterclockwise and go between 0 and pi over 2, so that when you start, let me make this motion. You are here at theta equals 0,
Oh, okay. Sorry, I got my
and
coordinates
counterclockwise to pi over 2.
I was like, I was like, yeah.
Yeah, so you go in the trigonometric sense. Here you have 8 minus, and who tells me what I'm supposed to type? R cosine theta minus R sine theta. And let Mr. whatever his name is, the computer, find the answer. Can I do it by hand? Actually, I can. I can, but it's not worth it because it drives me crazy. Okay? How would I do it by hand? I would split the integral into 3, and I would easily compute 8 times R integrand is going to be easy, right? Agree with me? Then what am I going to do? I'm going to say an R out times an R comes R squared. And I have integral of R squared times a function of theta only, which is going to be sine theta plus cosine theta. You say yes with a minus. With a minus, the heck with it, with a minus. Now, when I compute r and theta thingy, theta will be between 0 and pi over 2. R will be between 0 and 1. But I don't care, because Matthew reminded me, if you have a product of separate variables, life becomes all of a sudden easier for you.
I'm also going to add your integral of 8r here.
Yeah, at the end, I'm going to add the
Okay.
integral of 8r. So I take them separately. I just look at one chunk.
That's fine.
And this chunk will be what? Can you even see how easy it's going to be with naked eye? First of all, integral from 0 to 1 r squared, the r is a piece of cake. How much is that piece of salami? 1/3. Right? Because it's r cubed over 3, then you have 1/3. That's easy. With a minus in front that I don't care about in the end, what is integral of sine theta cosine theta?
Negative.
Minus cosine theta plus sine theta, taken between 0 and pi over 2. Well, will this be hard? Who's going to tell me how I'm going to get? What? We don't compute it now, but I just give you. Cosine of pi over 2 is 0. Sine of pi over 2
Oh,
is
yeah, the 1 plus
1. So this is going to be 1 minus, what's the whole thingy computed at 0? It's going to be minus 1, but minus 1 is plus 1. So I have 2. So only this chunk of the integral will be easy, minus 2/3 something. Okay? So it can be done by hand, but why waste the time when you can do it with Maple? Yes, sir.
We can get rid of 8 on the second after the 8 minus.
No, I didn't exactly. That's exactly what we were talking. Alex says, but you just talked about integral of 8r, but you didn't want to do it. I said, I didn't want to do it. This is just the second chunk of this integral. So I know that I can do integral of 8r in no time. And then I would need to take this and add that and get the number. I don't care about the number, just care about the method. Yes, sir.
Why are the limits from 0 to 1 instead of like 0 to r squared? Like, didn't we say earlier the domain is x squared plus y squared? Wouldn't that be r squared?
No, wait. This is r squared.
Right. Why didn't we plug r squared in where 1 is?
And that means r is between 0 and 1.
Oh,
Right? R squared being less than 1, that means r is between 0 and 1. Okay? And one last problem. No last problem. We have barely 10 minutes. So, you read from the book some. I will come back to this section and I'll do review. Have a wonderful spring break. And I'm going to see you after spring break on Tuesday.